Welcome to the deep dive. Today, we're looking at something pretty extraordinary. The January 15th, 2022 eruption of the Hunga Tonga-Hunga Ha volcano.
That's right. This wasn't just your typical eruption. Its impact was, well, much bigger and reached much higher than we might have expected.
Yeah, the findings show it had effects way beyond the immediate area.
Absolutely. We're talking about effects reaching into the upper atmosphere based on, detailed scientific analysis. It really challenges some ideas about volcanic reach.
Okay, so our goal here is to unpack that. Understand the sheer power, but also, crucially, the surprising effects way up in the thermosphere.
Exactly, that layer where so many of our satellites operate.
And for you listening, particularly if you're studying for the UPSC exams, this is a great example of, well, how connected global events are and how they impact technology. It's definitely relevant stuff.
It really is a compelling case study, connects earth science, technology, even policy implications, shows how one event can ripple outwards.
So let's start with the basics. Just how massive was this eruption? We're not talking a small event here.
Oh, far from it. I mean, the ash and gas plume shot over 31 miles straight up.
31 miles.
Yeah. To put that in perspective, that's way, way above where commercial jets fly. We're talking different layers of the atmosphere entirely.
Wow. And I read that this was actually higher than any other eruption recorded in the satellite era.
That's what the data indicates, a record setter in that sense.
Incredible.
But the really groundbreaking part is where those effects were felt, all the way up in the thermosphere.
The thermosphere, which is, what, 50 miles up and onwards?
Right, roughly 53 to 375 miles up. And that's prime real estate for low Earth orbit satellites, the ones doing communication, observation.
So the eruption's effects actually reached satellite altitudes. It's kind of hard to picture. What did scientists actually observe up there?
Well, they saw pretty dramatic and rapid responses at those altitudes, things changing quickly because of the eruption's energy.
Disturbances.
Yes, significant disturbances. It generated these waves that traveled upwards in a way that seemed, well, different from past eruptions. It showed a really strong link between the lower atmosphere and the very upper reaches.
Okay, but how do you even track something like that? An event on the ground affecting things hundreds of miles up.
Yeah, good question. Researchers, specifically a team from the University of Science and Technology of China, did some really clever work here.
What did they use?
They used satellite data, missions like GRACEO, and combined that with some pretty sophisticated atmospheric models.
Like computer simulations.
Exactly. Virtual Earths, basically, to simulate how the atmosphere behaves. This helped them trace the connection between the blast and what happened way up high.
So they had the data, they had the models. What mechanisms did they think could transmit that energy so far up? What were the candidates?
Well, they looked mainly at two possibilities: Lamb waves, which are a type of atmospheric wave, and also primary gravity waves generated by the initial blast. But what their analysis really pointed to, the main driver, was actually secondary gravity waves.
Secondary gravity waves. Okay, hold on. How are those different? Where do they come from?
Right, so primary gravity waves are like the immediate ripples from the explosion itself. The secondary ones, though, were generated later and higher up.
How?
It seems they were triggered when that massive volcanic plume, the one that went up 31 miles, actually punched into the mesosphere. That's the layer below the thermosphere.
Ah, I see.
So the plume hitting the mesosphere acted like a second huge disturbance, and that launched these secondary waves upwards.
So it's like a two-stage rocket effect almost. The initial blast, then the plume itself, creating more waves higher up.
Precisely. And what was really remarkable was how well these secondary waves traveled all the way up to satellite altitudes.
Which isn't typical for volcanic effects.
Oh, not usually, no. That region is normally pretty isolated from surface events like volcanoes. They found that while Lamb waves did play a role, these secondary gravity waves were definitely the dominant factor for those high-altitude effects.
Fascinating. It's almost counterintuitive. So what was the proof? How did they confirm this secondary wave idea?
Well, the evidence came from comparing the models to the actual satellite data. The speed and the intensity of the secondary gravity waves predicted by the models matched what the satellites actually measured.
Matched how well?
Very well. There's a specific model they use, Mesorecam-CM, and its simulations of these secondary waves lined up almost perfectly with the GRACEO satellite measurements.
In terms of timing?
Timing, yes, but also the amplitude, the actual size or strength of the disturbance waves.
So the simulations and the real-world data told the same story.
Exactly. That kind of consistency gives strong support to the idea that these secondary waves were the key mechanism carrying the eruption's impact so incredibly high.
Okay, so the data fits, the models fit. This eruption reached way higher than we thought possible. What does this tell us about, well, our planet and our technology?
I think it's a really powerful illustration of how interconnected Earth's systems are, from the ground right up to the edge of space.
That a surface event can profoundly affect these upper regions.
Absolutely.
Yeah.
And these regions are critical for our technology. The Tonga event is like a stark reminder of that.
And we're talking about technology that's fundamental now, aren't we?
We really are. Disturbances in the thermosphere, they can potentially mess with satellite operations.
Like what specifically?
Things like our communication networks. GPS navigation relies on stable satellite orbits. Weather forecasting models use satellite data. Disruptions up there can have real downstream effects.
So understanding this connection is pretty crucial.
Increasingly so, yeah, especially as we rely more and more on space-based tech. And, for anyone studying for exams like the UPSC, thinking about the vulnerability of critical infrastructure to natural disasters, well, this adds another layer. How do we ensure resilience?
Right, so studying Tonga isn't just about understanding volcanoes or the atmosphere in isolation. It's about safeguarding our tech, informing disaster planning, maybe even future policies.
Precisely. The better we understand how these powerful events impact the thermosphere, the better we can prepare, maybe even mitigate risks to satellites in the future.
And this was potentially the biggest eruption of the 21st century so far.
It seems that way, yes, which makes the insights gained from studying it incredibly valuable. It's a landmark event for Earth science and for understanding these bigger system interactions.
It really drives home how a single event can cascade through the whole Earth system, even impacting space near Earth. Okay, so as we wrap this up, what's the main takeaway you want people to remember from this?
I think the key thing is that unexpectedly strong connection, that coupling between a major event on the surface and the very distant reaches of our atmosphere.
And the potential consequences for our technology.
Exactly. It forces us to rethink just how interconnected things are and how far-reaching the impacts of these powerful natural events can be.
It definitely makes you wonder what other surprising connections are there within Earth systems? And thinking bigger, how can we better prepare for these kinds of powerful phenomena?
What questions?
And for you, our listener, especially if the UPSC is on your radar, notice how interdisciplinary this is. You've got geology, atmospheric science, technology, global impacts, all rolled into one event. Understanding these complex interactions is, well, it's vital for effective governance today.
Absolutely. It highlights the need for that continued cross-disciplinary research to really grasp these connections and build resilience. We need that holistic view.
Well said. So if you found this deep dive insightful, maybe particularly relevant for your UPSC prep, please do, like this, subscribe for more, and definitely leave any questions you might have in the comments.
We'd love to hear them.
The information we talked about today draws heavily on analysis reported in Sustainability Times. Thanks so much for joining us for this deep dive. We hope it gave you something to think about regarding our amazing, interconnected planet.